Welcome, radiant viewers, to Science and Spirituality. 4 billion years ago, Earth was far from being a hospitable place. There was a high-pressure atmosphere of carbon dioxide and methane, with virtually no oxygen, and acidic oceans with no dissolved oxygen. The surface of the planet was exposed to ultraviolet light, creating the unbearable odor of ozone. Nevertheless, approximately 3.5 billion years ago, life took off, starting with some single-celled organisms that managed to protect themselves under the rocks from the blazing solar radiation. And about 2.7 billion years ago, something remarkable happened. Oxygen began to accumulate in the atmosphere. The oxygen accumulation was due to algae, bacteria similar to their modern offspring cyanobacteria, which harness the sun's energy by converting carbon dioxide and water into energy-rich carbohydrates and oxygen. They invented photosynthesis, setting up the planet for more complex organisms, including you and me. Plants have incorporated algae as their own organelle to perform the efficient photosynthesis cycle ever since. No wonder photosynthesis is considered the most important chemical reaction on Earth. All the food and energy sources, including fossil fuels we use, come directly or indirectly from photosynthesis. At present, we only understand the basic mechanism of the process. If we could learn some bacteria and plant photosynthetic know-how, we could have an unlimited, sustainable source of energy for as long as the sun shines, and we even could mop up the excess carbon dioxide from our atmosphere. Dr. Greg Engel, a young physicochemist, along with a team of researchers at the University of California, Berkeley, USA, discovered quantum sun energy harvesting and transfer in photosynthesis, which explains the high efficiency and speed of the photosynthesis process. Today, we have an opportunity to learn more about this scientific advancement firsthand from Dr. Greg Engel. Currently, Dr. Greg Engel is assistant professor at the Department of Chemistry at the University of Chicago, USA. For his discovery, he was named by Scientific American, a leading U.S. science magazine, as one of the top 50 research leaders of 2007.
You've done a lot of research on photosynthesis. How close are we to understanding the process?
Oh, we've been working on this for over a century now, and huge amounts of progress have been made. But every time we delve into it a little bit deeper, we discover something new. So it's important that we look at this, and I think we're getting closer.
So can you tell us a little bit about your research? What has been discovered?
Oh, absolutely. When you think about photosynthesis, there are really two processes that you have to understand. One is the chemical process that was discovered by biologists in the 1950s and 60s and Melvin Calvin of how you actually produce chemical energy. But the process that happens first is what we're studying, how you funnel the energy from light to the reaction center so these chemical processes can go on. Classically, you think of an excitation happening at one place and the excitation just moves to another, and if it gets stuck, it has to move back in order to go forward again. Sort of like a maze. It has to choose only one path at a time.
And what have you discovered?
We discovered a new wave-like mechanism of energy transfer. This is hard to think about because it's a purely quantum mechanical phenomenon. But the way the energy seems to move is it occupies many states at once. So it's more like pouring water into the maze, where the water flows through all pathways and then drains out the other side. It doesn't have to explore one tunnel or another, but rather it can explore them all at once and feel all the different paths around it in order to make it to the reaction center very quickly and very efficiently.
So that's how the energy is transferred with almost 100% efficiency.
Yes, the quantum efficiency of this process is almost perfect, far better than anything that we can build. And that's really the driving motivation to understand this. How does the process work, and how might we be able to use some of the design principles demonstrated in nature in order to make man-made materials that would work with similar efficiency?
On what time scale does this happen?
The time scale of energy transfer in these systems is around 100 to 500 femtoseconds, and a femtosecond is a millionth of a billionth of a second. So it's extraordinarily fast, the same time scale as single nuclear vibrations.
So this is the first direct evidence that shows that.
Yes. There had been this idea that energy could move in this way for a long time. In fact, in 1932, Francis Perrin in Paris published a paper suggesting that energy must move this way. But by the 1940s, this theory had sort of fallen by the wayside, and it didn't seem necessary to explain the data that we had. Only recently, with the advent of new very short pulse lasers where we can directly probe the quantum mechanics of these systems, were we able to confirm that Perrin back in 1932 was actually right, and that we had been thinking about this system incorrectly for the past 70 years. So now I think we really understand how the energy moves through the system and how it can be so efficient.
Can we get into your experiments? I know you've invented a spectroscopic method, a technique.
Yes, we've created a two-dimensional electronic spectroscopy, and this uses a series of 3 very, very short light pulses to excite the molecule and then tell where the energy is sometime later. As you change the delay between the pulses, you can map out how the energy you put in moves through the system.
Our interview with Dr. Greg Engel and his discoveries about the process of photosynthesis will resume after these messages. You are watching Science and Spirituality on Supreme Master Television. Welcome back to Science and Spirituality, where we are discussing the latest research advancement in understanding life-giving photosynthesis with Dr. Greg Engel. Let's now take a short laboratory tour with Dr. Engel.
The entire system depends on this laser. This is where we create the very short laser pulses that we use to interrogate the fast dynamics in photosynthesis. That if you have runners on a track, you need a stopwatch that starts right when the starting gun starts if you have a short sprint. But if it's a marathon and you start your clock a couple seconds late, it doesn't make as much difference. So we use this laser to create very short laser pulses, and then we send the pulses down the table and use delay stages over here in order to control the timing of the pulses. And then they're all incident on a very cold sample that's stored in that blue cryostat on the far side. But the most important part is being able to excite the photosynthetic complex and then watch where the energy is a little bit of time later. And we use this coherent laser system in order to do that. Actually, the pulses are produced in this little box over here, but then the pulses are amplified to extremely high power in this laser system here. It's called a regenerative amplifier. And we use these very powerful, very short pulses to excite many of the chlorophylls very, very quickly. And by exciting lots of them at the same time, we can get a signal that's strong enough that we can observe it. So we use short, high-power pulses and send them down the table to interact with the chlorophyll. And this laser system uses a green laser. You probably see the green light in order to pump a titanium sapphire crystal. That titanium sapphire crystal is what creates the very short, high-power laser pulses for us, and they're very broadband. There are many colors in these laser lights. It's not like a normal laser pointer. In comparison for power, this red beam that comes out of this laser has a peak power about 500 gigawatts. That's about 10 to the 12 times stronger than a typical red laser pointer. And all of that energy that's contained in that high power pulse is condensed into about 40 femtoseconds of time. So 40 millionths of a billionth of a second. We deliver all that power onto the sample in order to make our measurements.
The experimental results can be visualized in the following picture that Professor Engel describes for us.
We create a two-dimensional map of the energetic states in the system to tell which ones are linked to which others. So you see all the states on the main diagonal, and then you can see the linkages off of the main diagonal in order to understand how energy moves from one state down to another state. This is what allowed us to see this wave-like transfers. We saw energy moving back and forth for far longer than we expected. It seems that this is not coincidental, that the protein that the plants and bacteria make actually protects this coherence and allows this wave-like transfer to happen. We didn't expect to see this. It was a complete surprise to us that the signal would last for so long. And by long, I really only mean 600 femtoseconds. Usually, you would expect this wave-like character to disappear very, very quickly, and then you have a classical sort of hopping mechanism. But instead, the protein structure in these complexes protects this coherence, this wave-like aspect of the system, long enough that the energy can then move in a wave-like fashion and test out many different possibilities at once, and know which energy path is better. And in fact, it samples all states, and the most likely state is the one with the lowest energy in the reaction center. So that's why the energy moves to the reaction center so quickly. When we see this wave-like transfer in the data, what shows up is sort of a signal that gets stronger and then weaker and stronger and then weaker. We analyze the pattern in order to understand which energy levels were involved in the process. And as we started to get into the very fine details of this, we saw that it exactly matched our prediction. If we treated this as a coherent system and a quantum mechanical mechanism as compared to the hopping mechanism, it would exactly match the data. That's what we're showing in that graphic. We show the protein structure itself, and then we draw lines from the aspect of the protein structure to the data so that your eye can see how the physical structure of this protein maps onto the electronic structure that shows this wave-like dynamic.
What a flawless natural design! The protein structure effectively isolates the excitation centers from all outside fluctuations in order to maintain a coherent wave-like energy transfer to the reaction center in the photosynthesis process. How exactly does Mother Nature do this? This is something that Dr. Engel and other scientists are continuing to investigate. We thank Dr. Engel for your important research that has allowed for a better understanding of the design principles in photosynthesis. Our conversation with Dr. Greg Engel on life-giving photosynthesis will continue next Monday, here on Supreme Master Television. Thank you for being with us for today's Science and Spirituality. Words of Wisdom is up next, right after noteworthy news. See you next time.